In our last unit, we discussed ways of calculating probability. Chapter 6 is about taking those probabilities and modeling their distributions. So in this section, we're going to be looking at discrete random variables. And if you'll remember, discrete just means that we're talking about situations that have a finite number of possible outcomes. So a probability model that describes the possible outcomes of a chance process and the likelihood of those outcomes. So what are the possible outcomes and what are the probabilities of those outcomes look like? It's just a probability model. So for example, in the last unit, we looked at that possible outcomes for the tossing of a fair coin 3 times. We actually used a tree diagram to come up with all of those possibilities. So the sample space for that chance process has 8 different possible outcomes. We have anything anywhere from 3 heads to 3 tails and every combination in between. Because there are 8 equally likely outcomes, the probability of each one of the outcomes is 1/8. So what we're going to do is we're going to define the variable x. And we're going to let x equal the number of heads that's obtained from those 3 outcomes. The value of x will vary from one set of tosses to another, but it will be some value in between 0 and 3. We could either have a possibility of 3 heads, a possibility of no heads, or any combination in between. So how likely is x to take each one of those values? It will be easier to answer the question if we group all of those possible outcomes by the number of heads obtained. So there's only one possible way that we could get no heads. That would be that all 3 are tails. If we look at the different outcomes, we see that there's 3 different possibilities, 3 different ways that we could get exactly 1 head. We either get it on the first flip, we get it on the second flip, or we get it on the third flip. Likewise, there are 3 possible ways that we could get exactly 2 heads. Either the first 2 are heads, the last 2 are heads, or the first and the last one are heads. And then finally, there's only one way that we could have 3 heads because all 3 of those flips would have to give us heads as a result. So if we take those outcomes and model them using a table, we can calculate the probability. So the probability of getting exactly no heads would be 1, because there's one way that can occur, out of 8 total possible outcomes. The probability of getting exactly 1 head would be 3 out of 8, because there are 3 ways out of 8 possible outcomes that could occur. Same with 2 heads. We could have 3 out of 8 outcomes that are 2 heads. And we would have only 1 out of 8 outcomes that would produce 3 heads. So that would be the probability of each of those outcomes. Then we can take those probabilities and we can create a histogram from them. So my horizontal axis here is just going to be the number of heads that we get. My vertical axis is going to be the probability of each of those outcomes. So I'm going to scale this axis to make sure that I have anywhere from 1/8 to 3/8. So I'm just going to use maybe every 3 units. So I'll go 3 units and then we'll have a possibility of 1/8. If I go 3 more, then we're at 2/8 or 1/4. If I go 3 more, then we're at 3/8. If I go 3 more, then we are at 4/8 or 1/2. And that's good enough since our largest probability is 3/8. Then my outcomes for heads are anywhere from 0, 1, 2, or 3. I'm going to make each of those bar widths 3 so that I fill as much space as possible. So my first possible outcome is 0. And the probability of that happening is 1/8. So for my bar for 0, its height will represent the probability, which is 1/8. My next possible outcome is that I'll have exactly 1 of the 3 flips that comes up heads, and the probability of that happening is 3/8. So for the bar for 1, its height is going to be its probability, 3/8. The next possible outcome is 2. So for the bar representing 2, again, its probability will also be 3/8. So the height there, again, will be 3/8. And then my last bar will be that I get exactly 3 heads. Its height will be the probability, which is 1/8. So we've taken all of the possible outcomes, we've calculated the probability of each of those outcomes, and then we translated those probabilities into a histogram that models that distribution. And we can use this information to answer questions about the likeliness of different combinations of these events. For example, if they ask us what is the probability that we get at least one head from the 3 tosses of the coin, then we could calculate that answer a couple of ways. One way that we could do it is we could take each of the outcomes that satisfies the condition and add their probability. So if we want the probability of getting at least 1 heads, we're saying that we're looking for the probability that the event X, being the number of heads obtained, is greater than or equal to 1. Well, that would include all of the outcomes that have exactly 1, because that would be at least 1, but would it also include all of the outcomes that have exactly 2 and all of the outcomes that have exactly 3. So we could calculate that probability by taking the probability that X is equal to 1, adding the probability that X is equal to 2, because that would also satisfy the condition. And we could also add the probability that X equals 3, because that would also satisfy the condition. So we said before the probability that X is equal to 1 is 1/8, plus the probability that X is equal to 2 would be 3/8, plus the probability that X is equal to 3. Oh, I'm sorry. Probability that X is equal to 1 is actually 3/8, not 1/8. So 3/8 is the probability of getting exactly 1. 3/8 is the probability of getting exactly 2. And the probability of getting exactly 3 would be 1/8. So if we add those together, we've got 3 and 1 gives us a total probability of 7/8. As we saw in the last unit, sometimes it's easier to calculate probabilities using the complement rule. So instead of looking at this as at least 1, we could look at the opposite. And the opposite of at least 1 would be the probability of getting no heads, or the probability of X being less than 1. So either the outcome is greater than or equal to 1, or it's less than 1. So if we use the complement rule, we could calculate this as 1 minus the probability that X is less than 1, or we could calculate this as 1 minus the probability that X would be 0, because that's the only outcome that would not satisfy the condition. That would be the opposite of getting at least 1, would be none. So then we would have 1 minus the probability of X being exactly equal to 0. And we said the probability of getting no heads was 1/8. So again, if we take 1 and subtract 1/8, we would also get 7/8. So 2 different approaches to that same problem. So a numerical variable that describes the outcomes of a chance process, such as X in that last example with the coin tossing scenario, we call that a random variable. So the probability for a random variable, the probability model for a random variable, we call its probability distribution. So we're just modeling the probability of each of the possible outcomes, each of the possible values of our random variable X. And we've learned several different rules for probability, but we only have one way of assigning probabilities to events. We assign a probability to every individual outcome, and then we can add those probabilities to find the probability of any combination of those events. This idea works well if we can find a way to list all of the possible outcomes. we will call a random variable that has a probability assigned this way a discrete random variable. In other words, we're saying there are a finite number of outcomes, and we can calculate the probability of each one of those outcomes. The probability distribution for a discrete random variable must have all probabilities that are between 0 and 1, because that's one of our probability rules before. And the probabilities must add up to 1, because again, that's one of the conditions for our probability. If we take each of the possible outcomes and add them together, then we have to have 100% of all of our individuals that fall in one of those outcomes. So the total of those probabilities will have to be 1, representing 100%. A discrete random variable x takes a fixed set of possible values with gaps in between. The probability distribution for a discrete random variable x lists all of the values. We call them x sub I, but that's each one of the individual outcomes, and the probability p sub I. So event 1, outcome 1, we call x1, and its probability we call p1. The second possible outcome we call x2, and its probability would be p2. The next possible outcome we call x3, and its probability would be p3, and so on until we've accounted for every possible outcome and the probability for each of those outcomes. The probabilities must satisfy two requirements. Like we stated before, each probability has to be between 0 and 1, and the sum of all of the probabilities in the set has to total to 1. To find the probability of any event, all we have to do is add the probabilities for those particular values that make up the event, like we did in the last example. So let's take a look at another example. It says that in 1952, Dr. Virginia Apgar suggested 5 criteria for measuring a baby's health at birth: skin color, heart rate, muscle tone, breathing, and response when stimulated. She developed a 0, 1, or 2 scale to rate each newborn on each of the 5 criteria. A baby's Apgar score is the sum of the ratings on each of the 5 scales, which gives whole number values ranging from 0 to 10. Apgar scores are still used today to evaluate the health of a newborn. So if in each of the 5 categories, the baby receives a score of either 0, 1, or 2, and their Apgar score is the total of the points, the scores that they received in each of those. So you could have anything ranging from a 0 all the way up to a 10. What Apgar score is typical? To find out, researchers recorded the Apgar scores for over 2 million newborn babies in a single year. Imagine selecting one of these newborns at random. That's our chance process. Define the random variable x to equal the Apgar score of a randomly selected baby 1 minute after birth. The table below gives the probability distribution for x. So in the table, we have each of the possible outcomes. The Apgar score can be anything from 0 to 10. Again, this is a discrete model because we have a finite number of outcomes here, anything from 0 to 10. The probability of each of the outcomes is given as well. So for example, the probability of an Apgar score of 3 is 0.008 or 0.8%. The probability of an Apgar score of 6 is 0.038 or 3.8%. And the probability of an Apgar score of 9 is 0.437 or about 43.7%. So we're going to use these probabilities to answer 3 questions. First, we want to show that the probability distribution is a legitimate distribution. So show that the distribution for x is legitimate, that it meets the 2 requirements. Then in part B, we're going to take that probability table and we're going to create a histogram for the probability distribution. Then we're going to describe that distribution. Remember from before, when we're describing the distribution of a histogram, we want to discuss the SOCs, the shape, outliers, center, and spread. And then in part C, it says that the doctors decided that an Apgar score of 7 or higher indicates a healthy baby. We want to know, what is the probability that a randomly selected baby will be healthy? So what is the probability that a randomly selected baby will have an Apgar score of 7 or higher? So what I'd like for you guys to do is to take a few minutes and see if you can answer those questions. Once you have them answered, then go ahead and come back and play part 2 of the video.